This video will focus on just defining a couple of terms that we need moving forward in this unit. I can define temperature, pressure, and kinetic energy. So when we talk about pressure, pressure is defined as a force applied to any kind of area. So whether you're talking about the walls of a room, or a person, or a desk, or a container that the gas is in, essentially pressure is when the gas strikes the object, the container, or the person. One thing to realize about pressure, we specifically focus on pressure of gases, but there's pressure due to liquids too. If you're submerged under the surface of water, for example, and then go lower, you can feel more pressure as you have more force applied by the particles. One thing you know about the word force, force in physics equals, for an equation, mass times acceleration. So when we think about pressure and how we can affect pressure, we can increase pressure by decreasing area, because pressure equals force divided by area, so decrease area, increase pressure. We can also increase pressure by increasing force, and since force equals mass times acceleration, if we have a bigger object or we have it accelerating more rapidly, in both those cases we can get more pressure. So I often think of pressure when it comes to jumping into water, right? If you dive into water and you apply pressure, all of your force to that tiny pressure of just your hands, you can slice right through the surface. But if you belly flop, right, you'll feel all of that force on you and lots of pressure. Pressure is measured in 3 different units, ATM or atmospheres, millimeters of mercury, which is literally a height measurement, and pascals. We'll talk a little bit about this in class, but essentially they're the 3 units we most commonly use. Millimeters of mercury was defined by the actual height mercury rises in a vacuum based on just the atmospheric pressure. And then ATM or atmospheres is defined by the amount of gases in the atmosphere pressing down on you. So both these cases I'm talking about something called atmospheric pressure. And atmospheric pressure is due to the gases in the atmosphere that are just pressing down on you at all times. So like as you're sitting watching this video, you have atmospheric pressure on you because that's how it works. You have gases all around you and they are applying force on you by hitting. We can convert between the units. Those conversions are down there on the bottom. I'll give those to you on a test if you need them, but you're going to need them like for any problems we do. Just have them as a reference. So I've mentioned atmospheric pressure already, and again, here it is defined. It's the pressure exerted on us due to all the gases in the atmosphere. Okay, so we have tons of gases in our atmosphere, and they're all pressing down onto the surface of the Earth. And when we talk about that ATM, that unit of atmospheres, ATM, the way it's defined as if we go to our outer edge of our atmosphere all the way down to sea level, and if you take a 1 meter squared column of all of the gases in that area, that's going to equal 1 ATM of pressure. So I like this image. I'd like you to have this image in your mind when you think about atmospheric pressure, because this image can help you understand why if I go up a mountain, I have less pressure. So if you go up a mountain, you're going to be up higher from the surface of the Earth. So if you think about the column of air pressing on you, you'll have less air pressing on you up a mountain. That's less pressure. If you went below sea level, you have more pressure pushing on you. So this is a good image just to remember. You don't need that definition that ATM is defined as a 1 meter squared column, but it's a good image to think in your head. If I ask you a question about going up a mountain, what has happened to the pressure? You should know that the pressure has decreased because you've gone up a mountain. The other term we need to start this unit is temperature. Earlier in the year, we talked about how temperature was a measure of kinetic energy, which is motion energy. But the word that we don't always have is average. So temperature is actually a measure of the average kinetic energy of any system. Again, kinetic energy is that motion energy, potential energy is the stored energy. Temperature has to do with motion energy. So the 3 words that are very interchangeable when it comes to temperature are energy, speed, and temp. So the higher the energy, the faster you move, and the hotter the temp. So those 3 things all have a direct relationship. If it moves faster, it's hotter. If it has more energy, it's moving faster and it's hotter, right? All 3 of these things go together. So slower will be colder and less energy always. Because temperature is a measure of average kinetic energy, that means it's an average of all the motion. If we actually graph the speed that a molecule is moving, so essentially graph the energy or the temperature versus how many of them are moving, what you're going to find is there is a range of possible energies, which means a range of possible temperatures, which means a range of possible speeds. So the idea that temperature is a measure of average kinetic energy, what that means is when you take the temperature of, say, water, the temperature of my water is at 15 degrees Celsius. What that means is the majority of the particles in your substance are moving at such a rate that they have a temperature of 15 degrees Celsius. But some are moving faster and some are moving slower. Okay? This graph is called a Maxwell distribution, and it shows you the distribution of the energies or the speeds or the temperatures of all of the particles in your substance. We'll spend some time on these graphs in class, but do note that first blue line, that's your coldest temp or your lowest energy, and you can see there's not as wide a range of possible speeds at which the particles are moving. So essentially, the colder your substance, the more narrow your range is, the more you have at your average, where the hotter you get, you see that my curve flattens out a lot and the distribution gets wider. So that means we're talking about gases that are surrounding you at all times. You might register that the gas in the air is measuring to be 23 degrees Celsius, but you have a very wide range of actual particle temperatures in the air. Some of those guys are so hot and some of them are so cold. That phenomena, the idea that not every particle is moving at the same speed or the same temp, allows for lots of things that we see, especially when it comes to changing states of matter. So that's it for this intro of these few words. Go ahead and do the form and have a nice night.